Welcome everybody. Topic of my work is interpolating salinity and waterlogging status using spatial analysis tools. My co-author is Dr. Mahesh Kothari, professor from Maharana Pratap University of Agriculture and Technology, India. So now, I would like to introduce you with the word salinity and waterlogging, as I know everybody of you must have heard this name. So salinity is the presence of salt in the root zone of the soil. There are two types of salinizations. One is primary and the other one is secondary, which I will describe in the coming slides. Now, waterlogging is the rising of water table. What are waterlogged soils? The soils which has surface layers completely saturated with water. As you all know, salinity and waterlogging generally occurs due naturally. They are they are naturally occurring phenomena, but irrigation raises and promotes this problem. The main reason behind the irrigation-induced salinity is inadequate drainage, leakage from poorly or unlined canals and reservoirs, and over-irrigation due to high concentration of irrigation water. Coming to the next slide. There are two types of salinization. One is primary salinization that occurs naturally, then the secondary salinization, which has again two parts, dryland salinity and irrigation salinity. Irrigation salinity causes salt accumulation in the soil, which requires to be leached out, which needs more water to be leached out. That causes rise of water table. Simultaneously, seepages from canals also increases the rise in water table. That leads to the capillary rise, and again coming back to the cycle, come back to the irrigation salinity. All this we can say that high water in plant roots limits removal of sodium and chlorine ions due to high concentration and transportation. That this ionic imbalance then finally causes soil impermeability and does not let the crops to grow, and effects reduces the crop yield. Now, why do we need a modeling of salinity and waterlogging? Although salinity and waterlogging there are various scenarios which are related to this salinity and waterlogging that can be experimented and examined through field experiments. But there are some vital restrictions which make these field experiments more deceptive. Like these field trials are valid to a limited area. We cannot take a big area at some point of time. We have to do it at different time, or the time is also bounded, as when we have crops grown on the fields, we cannot take the soil samples. So physical conditions in which tests have been conducted are also limited. Then it neglects the long-term effect of soil. You can only get the results of that point of that particular time of when you have taken the samples from the fields. You don't know that what was the condition earlier and what is going to be in the next year or in the next 10 to 20 years. So this neglects the long-term effect of salinity and waterlogging problems, and they are normally performed for a very short duration of time. So overcome all these limitation of field trials. Nowadays we have very well tested and verified simulation models which are easily available, free on you can download it from the sites, and which can be applied as an extension to the field experiments are set to solve the queries related to salinity and waterlogging problems. Now, what is the role of GIS? As we all know, salinity and waterlogging, they are both temporal and spatial. So the modeling of salinity and waterlogging gives us the temporal results. You can get the results for next 10 years, for 20 years, but spatially it does not give. You will get the results for that particular point where you have collected the sample. Non-sample point, you cannot get the results. So for that spatial analysis, we use GIS techniques, which are quite efficient method to solve this problem in allocating the salt affected soils. So GIS is being a powerful tool in the natural resource inventory and data handling. Also, it has appeared as an improved speed and precise and quite cost-effective technology, as they are easily available. They are quite, you don't have to pay a lot for this, all these softwares. So its application in mapping and monitoring degraded lands, especially the saline soils, are very, very effective. Next, What is my aim? My aim is, the main aim is here is the spatial analysis. I have done the temporal analysis through the modeling. I have collected the observed data. I have predicted the data. Now what? The sample points are there, their data are there. I can suggest the farmers who having their fields in that sample points, but I cannot suggest the farmers who have whose samples have not taken. The problems occurring in that area also. So for which I have used the GIS techniques. I've interpolated both the observed and the predicted data. Then I overlaid the salinity on the land use land cover maps, which are known as LULC maps. So what we do in LULC maps, it's just that interpolating observed and predicted data only gives you the spatial distribution of the salinity and waterlogging, but you don't know where the barren land occurs, where is the river, where is the crops like mustard, rabi crops like wheat, mustard, whatever we are growing. We don't know what is the condition of the salt at what point, although it is more in wheat or it is more in mustard or it is more in barren land. So we have overlaid this interpolated maps on LULC maps. Then further, finally, I have classified the severity classes of these saline and waterlogged conditions. In saline conditions, I have classified it as saline, non-saline, saline, moderately saline, and highly saline. In non-saline area, it is between 0 to 2 decisiemens per meter. Low saline area lies between 2 to 4 decisiemens per meter. Moderately saline is between 4 to 8, and high salinity is between 4 to 16 decisiemens per meter. Similarly, is the case with waterlogged soils. There it is the less than it when water table is less than 2 meter. It is non what it is the it comes under safe area. Then between 2 to 3, it is between potentially it occurs in potentially waterlogged area, and above 3 meter it is highly waterlogged area. Coming to the next, this is my study area. You can see Chambal command area, which is my study area. It is a tributary of Yamuna, and it originates from the Bhatkala Falls in Janpav Hills, Vindhyachal Ranges, Madhya Pradesh. Its total length is 1,024 kilometers. It flows in different states. In Madhya Pradesh, its length is 376 kilometers. In Rajasthan, it's 249 kilometers. In between Madhya Pradesh and Rajasthan, it is 216 kilometers. Madhya Pradesh and Uttar Pradesh, it is 150 kilometers, and in Uttar Pradesh, where it ends, it is only 33 kilometers. So amongst from these three main states, our concern is in the Rajasthan, where it has four dams constructed on it. One is Gandhi Sagar, Rana Pratap Sagar, Jawahar Sagar, and Kota Barrage. The first three dams are used for power generation. Last Kota Barrage is used for irrigation facilities. For Kota Barrage, Kota Barrage supplies water to the Chambal command area. It has two main canals. One is right main canal, other one is left main canal. Right main canal is total length in Rajasthan is 124 kilometers with a design discharge of 188 meter cube per second, and the left main canal is length is 2.74 kilometer with 42 meter cube per second of design discharge. Now, this is the of the study area. You can see the area is around 91,040 hectares, and its latitude lies between 25 degree and 26 degree north. Longitude lies between 75 degree and 76 degree east. The region is semi-arid. Climate is subtropical. Its average rainfall is 800 mm, and maximum temperature recorded is 45.8 degrees Celsius in May, and minimum temperature recorded is 7.5 degrees Celsius in January. Soil is clay to clay loam. Three kinds of crops are grown: Kharif, which is the rainy crop; Rabi is the winter crop; and hot season is the summer crops. Generally, in the hot season, crops are not grown in this area. This is the area you can see here. This is the command area. This is the right main canal flowing. The above part is these are the minor sub branches. This is the whole command area. This is the non-command. I have also taken some points from the non-command area, because I've got the complaints from this area also, that due to seepage from the canals onto the other side also, the problem of salinity and waterlogging has started arising. In the command area, I've taken several samples. Now, this is the complete picture of Chambal command area. This is the picture of the Reitman Canal flowing. The total gross command area of this command is 4,85,000 hectares. Culturable command area is 2,29,000 hectares. District-wise distribution is in the Kota district is 95,000 hectares, in the Baran district is 35,000 hectares, and in Bundi it is 99,000 hectares. This command, Chambal command area, in the Chambal command irrigation has started in the year 1960. Since then, the problem has been observed. Problem of salinity and waterlogging has been observed. It has been worsened by undulating terrain and improper water management and conventional farming practices. So, problem of salinity has reduced the crop production. Some of the land has started going out of cultivation, wastage. A lot of water has been wasted. Irrigation water has been wasted due to the over irrigation, and land and water quality has also been degraded. So, in say by 1970, 25,000 hectare and 1,61,000 hectare of the area has got saline and waterlogged respectively. So, for to cope up with these problems, by in the year 1967, land and water management use program with the help of UNDP and FAO has been introduced in the area. The main aim of this program was finding various means to solve salinity and waterlogging problems, developing proper water management practices, and giving suggestions for proper land and water management. So by 1970, this program was supported by the World Bank, and another program has been introduced, which is known as the On-Farm Development Program, which is still in the process. It has got very good results. So this has increased the difference in the on-farm irrigation and surface drainage. The main aim of this program was to increase the efficiency of on-farm irrigation and surface drainage. Even the problem, but after implementing this also, some of the area which has been treated by on-farm development programs also finding the problem of land, because it has solved the problem of surface drainage as well as on-farm irrigation, but the subsurface area has not been treated by this on-farm development program. So therefore, finally, a project called Rajasthan Agricultural Program of agricultural drainage has been introduced, which was executed it was a joint venture between the Canadian International Development Agency, a joint venture between central and the state government and the Canadian government. The main aim of this project was to implement a large scale of horizontal subsurface drainage systems and related water management techniques to control irrigation induced soil salinity and waterlogging. The area which was selected was 53 hectares, and it was implemented on those areas which was already treated by the on-farm development programs. Here you can see the area, the work on-farm development works completed in the study area, and the subsurface drainage blocks in this study area. Now, next is my methodology, what data I've used, what process I've gone through, what softwares has its utility in this process, and what output I got. First of all, I have used the satellite images. With the satellite images, I have done the unsupervised classification using ground truth data and decoding operations. Using the EDAS Imagine 9.2 software, the output I got was the land use land cover map. Then, using these land use cover maps, observed and predicted salinity and water table depth data, I have reclassified this LULC map in ArcGIS 10.1, where I got the reclassified LULC and saline and waterlogged maps. Then, further using this reclassified land use, land cover, and saline waterlogged maps, I have classified the severity levels and overlaying process where I've overlaid the LULC maps on saline and waterlogged maps using AGRI Silva software. These overlaid EC and LULC maps were used for final preparation for polishing in the ArcGIS 10.1 software. Then we got the final maps of electrical conductivity, which shows the salinity, and the water table depth map, which shows the waterlogging conditions. Next, this is the land use land cover map of the study. You can see the barren land settlements, dense vegetation, and water body. This shows the general classification of the area. The wheat area and the mustard area is this LULC map is of the for the Rabi season, where the wheat and mustard are the major crops. Now, these are the pictures representing the AGRI Selva process. First is the reclassification of maps in AGRI Selva on the basis of severity levels. Then projection of maps in AGRI Selva as per LULC dimensions. This is this. Now the projected met output in AGRI Selva as per LULC dimensions. Finally, the overlaid EC and LULC maps in output in AGRI Selva. These maps were then exported to ArcGIS for further classification. Here, by overlaying EC and LULC maps on EC, we have done the area calculation. You can see here as per barren land, wheatland, and wheat crop and mustard crops. How much area has been salined in barren, how much in mustard, how much in wheat. Here are my results. So you can see I have collected sample data for 54 sample data at 3 depths, 0 to 30, 30 to 60, and 60 to 90. Then after collecting, analyzing them, then calculating the EC values, I have got the results. Then I've interpolated and prepared these maps. So from the maps output, we can make out that the non-saline area is more at present and low saline area is less. Right now, there is not the area has not been affected by moderately as well as high salinity. Now, from the modeling, from the model, I have used a salt mode model for this prediction. The model has predicted 10th year and 20th salinity values for all those 54 points, but that was not sufficient to make out what is the salinity condition. So I have prepared the predicted root zone map after doing the geostatistical and geostatistical analysis of the data. So you can see here some area in the 28th year is found in moderate, found to be in the range of moderate salinity and very small area. You can see here the patch for which is near, which this area is lying near to the river. It is in under high salinity. Okay, of course, the low saline area, this low saline area from this is changed to the moderately saline section. Also, you can see the non-saline part has also increased because of some of this part, as I've already shown you, the subsurface drainage system blocks. This area was under that. Considering the sub SSDs for at some points, the results have shown that some of the area which is in a low salinity would also come to the non-saline. Now, here you can see the graphical representation of barren land, wheat, and mustard land. So, Most of the part of barren land, mustard and wheat is under, at all the three depths is under 0 to 2, which is non-saline part. Very little part is under the moderately saline section range. It's around between 10 to 20% is under moderately saline, and rest 80 to 100, 80 to 90% it is non-saline. Now, next, we have divided the observed, graphically presented the observed 10th and 20th year predicted data. So we can see that here in the year observed data, 88% of the area is under the non-saline part, while in the 10th year it has decreased, and further into 20th year it has come to 1%, while high rise in the moderately saline, low saline section, which has increased from 12 to 93. Then in the 20th year it has decreased to 71%. Area under moderately saline and high saline in the observed year was 0, but has increased a slight, it has slightly increased in the 10th year, and then a good increase has been observed in case of moderately saline area, which is 26.2%. This slide is particularly for the barren land. So you can say that in the land where there is no crops grown, the salinity is increasing with the years, with the passing years. Now it is for this is for wheat. So you can see in wheat section also, non-saline area has been decreasing, low saline area is increasing abruptly, while moderately and high saline area has also shown a moderate increase. It has reached to 18.4% in 20th year. Now coming to the mustard crop, again the same kind of trend as of wheat and barren land. You can see the non-saline area has decreased from 92 to 12th in 10th year. It has increased again in the to 17% in 20th year. Also, the low saline area has increased from 8 to 88%, and it has decreased again from to 88 to 65%. Actually, the model works on the concept that if the points I have used the SSD, presence of SSD, it would consider to work slowly, gradually. So in the beginning of the first 10 years, it would show you the increase in the value of salinity and then a decrease. Although it is decreasing, but the values are not very good. 65% of the area in low salinity is quite, you have to work on this. You should take the, because the most 92%, because simultaneously the area which is 92% non-saline today is also decreasing. Now the, as of, it is not possible to measure the transition shown salinity, but the model predicts the transition salinity. So for the 10th and the 20th year, which for that also I have prepared the maps. So you can see here, most of the area is under non-saline in the next 10 years. Some of the area is under low saline range. Further classification as per barren, wheat and mustard, you can see here around 37% area is between 2 to 4, which is decreasing in the and 63% is in the 10th year, which is under low salinity, is decreasing from 37% to 63%. Yeah, of course. Coming to the only the barren land. Okay. In the 10th year, 0 to 2, which is the low salinity area, it is 63%. While in the 20th year, the same is has rise to 66%. And the low saline area has decreased from 37% to 34%. Similarly, is the case with wheat, where 29% of area which is under low salinity would increase to 77% in the 20th year. So, okay, transition zone is showing good results because the SSD pipes which are installed in the on farm development crop area was in the almost in the transition zone, which is 1.2 meter below the soil depth, considered as the transition zone. So the model has shown us the results for a decrease in the salinity values. Now these are the water table depth maps. You can see lot of safe area, then the potentially blocked area, and then the waterlogged area. The area below to depth below 2 meter is under waterlogged conditions. 2 to 3 it is potentially waterlogged, and above 3 meter it is safe. The area which is under safe, which comes under safe area, has been treated by SSDs. Also, this part is also has also been treated by OFD programs. But you can see only treatment by the OFD program does not protect the land from getting waterlogged. You can see in the 20th year, the area which is under the safe, which is under safe conditions, has come to the potentially waterlogged condition in the 20th year. Also, some part of this has also come in the waterlogged condition. Okay. Now you can see in the barren land waterlogging conditions. The area between 2 to 3 meter, which is potentially waterlogged, has been increased from 24 to 28 in the 10th year, than in 45% in the 28th year. While highly waterlogged conditions has been decreased from 71 to 67, then to 15, as of the land which is barren has a space, has drainage system available for moving of water. Then for the wheat crop, you can see an increase, first a decrease in the potentially waterlogged condition in the 10th year, then just twice percentage of area has been affected by waterlogging conditions. Also, highly waterlogged area is decreased from 8 to 5%, then to 6%. Then for the mustard crop, you can see the potential highly waterlogged area has decreased first in the 10th year, then in the 20th year also, because mostly because the mustards are grown in the area where there is as OFD program has been, the area has been treated by the OFD programs as well as by SSDs. Also, you can see in the 20th year, the safe area is decreasing from 67% to 57%, while potentially waterlogged area is increasing from 36 to 26 to 36%. Quite significant, it's quite important. to look into this. My inferences from the work is that spatial analysis help in estimating aerial expansion of the problem. It becomes quite easy and convenient for us to to analyze the problem spatially as well as temporally. It enables the delineation and classification of saline and waterlogged area. Severity classes prioritizes the problematic area for kind and method of treatment required. With this severity classes, you can find out what kind of treatment you should give. It is in the potentially waterlogged area. If it's not required, you don't have to install the SSDs, as it is quite costly, and you can treat the area with on-farm development. Also, you can do it, you can protect it by doing the lining of the canals or the field channels, or other treatments. Some water management practices also, you can use some proper water distribution systems you can use for a proper distribution of water into each and every field, so that the area does not get waterlogged so easily, so at the portion of tail especially. Now, what I recommend, that intensive study of the non-treated command as well as non-treated command area as well as non-command area, because I have found several complaints from non-command area also, that salinity and water logging is causing the water has been collecting in their fields, and due to their saline conditions, their crop production has been decreased. Suitable treatment like on-farm development works, subsurface drainage system installation, water management practices, lining of canals, adequate drainage system, or lining or monitoring of the water distribution system should be applied in the areas which has been affected, or precautionary measures should be taken in the areas which not yet had been affected by this problem. Area which are already treated and it has subsurface drainage system installed, it should must be reevaluated for present conditions of the system. Thank you very much for your patience listening. This is my email. If you have any doubts, you can mail me or you can ask me now.